Okay, I'll make a start. So we've been looking at species interactions in continuous time recently. Today and Monday, we're just going to take a slight detour into some discrete time models of species interactions to show that some of the things that we've been looking at, whether it's resource competition or some sort of antagonistic consumer resource relationship, these can also be modeled in discrete time and how we might go about doing that. And then we're going to move back to continuous time models when we're focusing on infectious diseases. So today we're going to be looking at a predator-prey model and seeing how we can construct models in discrete time for species interactions. Look at this predator-prey model, which is the Neubert-Kot model. Talk about something called a Neimark-Sacker bifurcation, which is analogous to a hop bifurcation, and seeing just how this predator-prey model relates to some of the ones that we've looked at previously. Okay, so like I said, so far we've looked at functions of this form here. So we've got a system of two ODEs that are coupled, dx dt, dy dt, some functions f of x, y, and g of x, y. We can write something analogous in discrete time, where now we have xt plus 1 is equal to, here I've written it as xt plus f of x dy t, and likewise y of t plus 1 is equal to yt plus g of x dy t. This is one way of writing it. We don't always necessarily write them in this way. This is so that these functions here are analogous to the ones above. We might instead just have just f of x t y t or g of x t y t. So we could combine those in there. Of course, if you just had a minus xt in here or a minus yt, it would be the same thing. Okay, so we can construct these models here. If we let this time step shrink towards 0, we would regain those continuous time models. Okay, so just to make sure we remember why we might want to distinguish between discrete and continuous time models, why might you want to model here two species in discrete time? Yeah.
They have kind of like a nice like cycle structure to their births and deaths.
Yeah, so if there's like the big reason that people often talk about is seasonality. Like if there's some strong synchronicity, so seasonality slash synchronicity in terms of things like, yeah, births and deaths. Okay, so that's the basic idea. We're going to go through today a predator-prey model, and then on Monday we're going to go through something called a host-parasitoid model, which is somewhere between a predator-prey model and a host-parasite model. Okay, so this model was from a couple of authors from the early 90s, and they were modeling predator-prey interactions in discrete time, so classic consumer resource situation. And the model is nt plus 1, where nt is our prey population size in year t. So nt plus 1 is going to equal nt, so what we have in the current year, plus r, where r is the intrinsic per capita growth rate of the prey, times nt, that's by 1 minus nt over k. K is our carrying capacity, so we've got some logistic growth going on here. And then minus c nt pt, where pt is the density of our predators. So we have this predation term on the end. It's a Holling type 1 predation term, so it's linear. And then our predator population, pt plus 1, is just equal to b, where I realize I haven't actually written down what b is down here, ntpt. So b is reproduction or births for our predators. And it is based on consuming resources to consuming prey. Okay, so that's the basic structure of this model. Yeah.
How come for pt plus 1 we don't have it as like pt plus?
Very, very good question. So this would be an example where it's not set up like this. Yeah. Or in fact, our g of xt yt here is technically bnt pt minus yt. So if you think about it in that way, if you think of this as some function g of xt, oh yeah, if we set our g of xt yt Terrible subscript there. Let's do that again. G of x t y t is equal to b n t p t minus y t. That might help you answer that question below. That leads very nicely onto that. So what happens to predators in year t plus 1 who are alive in year t? It's kind of hard to see it from just the b n t p t equation, but if you think about this function g, which you very nicely segued me into, thanks for that. This term here, right, what's this going to represent? This b n t p t from the predator's perspective. Yep, so it's a growth rate that consumes some resources and that allows them to reproduce. And what's the other term would be? Yeah, so you can think of this as basically births and deaths. So because this is in a discrete time, if I had, say, the death term was actually, say, something like minus d times by yt, what would the values of, where would d have to go between? What possible values of d could we have?
0 to 1.
0 to 1, right? And why is that?
You can't like have more deaths than population.
Exactly. So d would have to go between 0 and 1. So what's our d in this case? Okay, so what happens to all the predators alive in year t plus 1 who are alive in year t? They die, right? So this is set up as a model where all of the predators only live for 1 year in the next year or generation, depending on how you want to look at these time steps. And so there is this very strong synchronicity, right? There are cohorts, we have non-overlapping generations. So everyone in a cohort is born at the same time, lives through that year, but then they all die. For example, they might die in winter, right? They all die in winter, but if they produce eggs that survive over winter, then the next generation will come up. Okay, so again, this is one of the reasons why in this type of setup, you'd want that the discrete time model is better than the continuous time model for populations that might behave like this, because you have these very strict separation between these cohorts, so these non-overlapping generations. So what happens to all the predators? They all die. So we can do some of the same tricks that we did in continuous time, in discrete time. So we can use non-dimensionalization again. So let's non-dimensionalize this model and eliminate some parameters, make it a little bit simpler. One thing we can't really do now is we can't non-dimensionalize according to time, right? Previously, we would say adjust our time step. We'd maybe start off with d capital T and then rescale time, we end up with d little t. We can't really do that here because we've got these finite time steps, right? So in theory, you could kind of stretch them, but it's harder to do in this sense. So typically, we're just going to rescale our population sizes and combine parameters where we can. So I'm going to define xt to be equal to nt over k. So this is basically saying xt is going to be my prey population relative to its carrying capacity in the absence of predation. So what does that look like? So previously we had pt plus 1 is equal to b times by nt pt. So we can write pt plus 1 is going to equal, we had b, we had an nt, so we're going to replace that with k times by nt now, and then we keep that pt there. And let's think about our equation for nt plus 1. So our xt plus 1 is just going to be k times by our nt plus 1 equation. And our nt plus 1 equation is just this above. So let's copy that. So this is our equation here. And we're going to have k times by this. Okay. So oh, sorry, I've made a mistake. This shouldn't be times by k, this should be dividing by k. Xt plus 1 is equal to nt plus 1 over k. So we should have a 1 over k. Sorry about that. Okay, so everywhere we see an nt, we can replace it with k times by xt. So kxt here plus rk xt. We've got an nt over k in the brackets, so we're just going to have 1 minus xt here. And then we're going to have a c kxt pt. And then we can see all of our k's are going to cancel. So that's all quite nice. And then if we were to expand out this bracket, so we've got xt plus r minus r xt. I got here some, made a mistake here somewhere. No, I'm good. Right. So we're going to have 1 plus r times by xt. We're going to have a minus xt squared, and minus rxt squared even. And then we're just going to have the minus c xt pt. We could leave this pt as it is, but we could change things around a little bit, which will make the analysis slightly easier for that as well. So if we let yt, this is going to be our rescaled predator population, equal cpt over bk. Then in that case, if we go back to our xt plus 1 equation, we're going to have 1 plus r times by xt minus rxt squared. So that hasn't changed. Then now we have this cpt here. We can replace that with, let's see what we'll have. We'll have minus bk xt yt. Okay, so that's just substituting this in for this pt here. So cpt is going to equal bk times by yt. So that's where that comes from. Oh, sorry.
If we go back up to the predator one there, we wrote bknt pt. Should it be?
Yes, thank you. Yeah. Well spotted. bkxtpt. See if I... No, I did have it right in my notes. I just wrote down the wrong thing. Okay, thanks for that. Okay, so what can we do? We can combine this b and the k. They appear together, so we can just collapse them down into one parameter. So we're now going to have 1 plus r xt minus rxt squared minus, let's call it a xt yt, where a is equal to bk. And then if we noticed in this equation up here, we had a bk as well. Then yt plus 1 is going to be equal to, well, yt plus 1 is equal to c times by pt plus 1 over bk. That's from this equation here. So let's just write that down first before we get too far ahead. So we need c pt plus 1 over bk, which is equal to c over bk times by pt plus 1 up here is bk xt pt, bk xt, and then pt, we are going to have, let's see. Make sure I've not made a mistake here. XTPT. Yeah, that's fine. Everything's going to cancel. Okay, so we get another BK here and a PT over C. Okay, does that make sense what I've done there? I'm just making sure I didn't have any mistakes in my notes.
Is that a YT?
It is, thank you. I keep writing the wrong ones down, even though they're in my notes. I'm just checking you guys are paying attention. That's what it is. Okay. So the C's cancel, one set of the BK's cancel, and then we can just write this as A XT YT, because we just end up with a BK at the front and we defined A is equal to BK. Okay, so we end up with these equations here, which are a little bit simpler. We've lost our K's. It's a little bit easier to analyze than before. The same basic process applies though. You know, we're substituting in some parameters to try and eliminate some, and usually substituting things like carrying capacities in are a pretty good one to do. Okay, steady states. So just like in one dimension, our steady states we can write down for our discrete time systems in 2D. So we have a pair of states x star, y star. We say that's a steady state of some functions xt plus 1 is equal to, and this time I'm just going to write it as f of xt, yt, and yt plus 1 is equal to g of xt, yt. If f of x star, y star is equal to x star, and g of x star, y star is equal to y star. Hopefully that should be fairly intuitive. In one dimension, we just had f of x star is equal to x star. Now we're in 2 dimensions, so we need to have f of x star, y star is equal to x star, g of x star, y star is equal to y star. Again, in continuous time, these would be equal to 0, but because we're in discrete time now, we want our left-hand side and right-hand side to balance being equal to x star, okay, or y star. Okay. I assume have you guys all written down the non-dimensionalized version of the model I've got here? What I want you to do is have a go and see if you can find the steady states for this model. I'd suggest starting with the equation for y, because that's a little bit easier. Okay. So have a go at that. I'm going to walk around and see if I can help you guys. If you have any questions. Yeah, I think you don't in a ever so slightly different way, and I can't quite see what's different. What I'm gonna just for time's sake, I'm gonna start working through it, and then maybe we'll spot the error afterwards. Okay. Okay. You guys are right to me to go through? Okay, so let's start with our y star. It's gonna equal ax star y star. So that's just from this equation here, setting that equal to y star. So if that's true, then we either need y star to be equal to 0, or we divide 3 by y star because it's non-zero, in which case we're going to have 1 is equal to ax star y star. No, sorry, 1 is equal to ax star. So we've divided 3 by y star. So we can just rearrange that as equal to x star is equal to 1 over a. So these are our 2 values that tell us about our steady states from our first equation. Let's consider what happens if y star is equal to 0. Then our equation for xt plus 1, we're going to have x star is equal to, just write it out in full to start with, 1 plus x star, sorry, 1 plus r times by x star minus r x star squared minus a x star y star. If y is equal to 0, we can drop this one off here. See. I'm going to leave it in there though. If we divide this equation here by itself implies that x star must equal 0, or we can divide 3 by x star. Okay, so if we divide 3 by x star, we'll go to 1 is equal to 1 plus r minus rx star minus a y star. So I think this is probably what did you end up? Did you end up with a 1 minus r in your brackets? You'd had r times, or did you have an r times by x minus 1? Is it rx times by x minus 1? Confusing me now, man. It's fine. No, it's fine. So this is true. I think the problem is this: if y is equal to 0. Let's ignore that for a second and just focus on what happens if we were to set this equation equal to x star. Okay, so this is from my xt plus 1. So from that equation by itself, we know that x star must equal 0. Probably would have been easier if I just did this equation first rather than the one above, which is probably kind of confusing things a bit. Our x stars must equal 0, or this thing here must be true. If my x star is equal to 0, I know from this equation up here, if I go backwards, y star must also equal 0. Okay, so it's pretty easier if I had done it the other way around. So x star is equal to 0 implies also that y star must equal to 0. Okay. If I then think about this second one here, if x star is non-zero, what if x star is non-zero? Well, we know from this equation up here that x star must equal 1 over a. That's the only possibility for if y star is non-zero, x star is going to be x star must equal 1 over a. Okay. So if x star is equal to 1 over a, then we can substitute it into this equation here. Then this one here. And 1 is equal to 1 plus r minus r over a minus a y star. We can subtract 1 from both sides. R minus r over a minus a y star. Divide by a. We get r minus r. Sorry, r over a minus r over a squared minus y star, which we can rewrite as y star is equal to a minus by r minus r over a squared. And then just factor out the r to be r times by a minus 1 over a squared. So when x, put it in here in brackets, when x is equal to 1 over a, then y star is equal to r a minus 1 over a squared. And when is this biologically realistic? Yeah. So a must be greater than 1 for it to be biologically realistic. I will go back over those. I'm pretty sure like the end result is right here, I think. I'll go back over my working afterwards and just check the notes to make sure that there isn't a mistake in there. In which case, if there is, I'll just post an update online, okay? I know that this non-trivial equilibrium at the end is definitely right. I don't know a non-trivial steady state. I should say I don't think I missed one, but if I have, I'll go back and update the notes, okay? I want to make sure we have. Oh, I know what's happened. There is another one.
I got one.
There should be x star is equal to 1 over a and y star is equal to 0. There is another one. That's why I have missed one out. So there should also be a pray only one of 1 over a 0. That's pretty where we were. There should have been that one as well. I will go back and I will make sure the notes online are properly updated to reflect this, okay? I want to move on and think about stability. Make sure we cover this today. So just like in our 2D case in continuous time, we can think about a small perturbation and see whether that perturbation grows or decays in discrete time. It's a little bit different because just when we did our simple population models before, where in continuous time, our solutions had the form e to the lambda t, where lambda was an eigenvalue. Here, our solutions contain terms of the form lambda to the power of t. Okay, so geometric rather than exponential. And so that just means that our threshold for stability switches, right? So when we have exponentials with our eigenvalues, we need our real part of those eigenvalues to be negative in order for those perturbations to decay. So you have e to the minus something times by t, and t gets very, very large, those perturbations decay. Therefore, you move back to a point, perhaps you're oscillating, perhaps you just move in sort of a monotonic fashion. but those perturbations decay. And so our threshold in continuous time is the real part of our lambda being equal to 0. So that's the threshold for stability and instability in 2 dimensions in a continuous time model, but in a discrete time model in 2D, we now need to think about the modulus of this lambda being less than 1. Okay, so if we're taking something here to be less than 1, parity, we want that to be shrinking over time. So it needs to be less than 1 here. It could be negative, but as long as it's between -1 and 1, then this will shrink over time. They can also be complex conjugates now, so we're thinking essentially about the length of our real part and our imaginary part squared and square rooted to give us this value of lambda modulus here. Okay, so our stability thresholds have shifted essentially from 0 to 1. And in our continuous time models, we didn't always necessarily need to find our eigenvalues to work out what stability was, right? We could use the Ralph-Hurwitz conditions, where we just look at the trace and the Jacobian of our, the trace and the determinant of our Jacobian, and then look at the signs of those. And if the trace was negative and the determinant was positive, then we would have an equilibrium that was stable, okay? There's something analogous, a little bit more complicated in discrete time. These are called the jury conditions. But these, again, are telling us something specific about our eigenvalues of a matrix. Okay? So there's nothing intrinsic about the matrix itself that tells you whether you're in continuous or discrete time. But the Ralph-Hurwitz conditions tell you when your eigenvalues have negative real parts and therefore are stable. The jury conditions tell you when your eigenvalues of a matrix have absolute value less than 1. Okay. So what are these jury conditions? Well, if we have a 2x2 matrix, J, to have both of these eigenvalues having absolute value less than 1, and therefore x star, y star, some point corresponding to that Jacobian, is asymptotically stable. Asymptotically means that you're moving towards it. That only happens if and only if all 3 of these following conditions hold. So we need the trace of our Jacobian to be less than 1 plus the determinant. That's our first condition. We need minus the trace to be less than 1 plus the determinant. And we also need the determinant to be less than 1. These seem kind of arbitrary, coming out of nowhere, but I'll show you geometrically what's going on in a moment. We can actually write these all as one inequality. If we note that we've got something very similar here, 1 plus the determinant on the right-hand side, and we've got the trace and minus the trace on the left-hand side. So that's just the same as saying the absolute value of the trace is less than 1 plus the determinant. And over here, we need the determinant to be less than 1. Therefore, if we add 1 to both sides, we'll get 1 plus the determinant has to be less than 2. So we can write this all in one big inequality here. So it's often read in this form here, or you can split it out into these 3 separate conditions. But it's important to remember, regardless, if you end up seeing this, this is 3 inequalities. These 2 things are equivalent, right? So where does this all come from? Well, our jury conditions are telling us something about the eigenvalues of our Jacobian. Remember, if we want to find the eigenvalues of any matrix, we need to look at our characteristic equation where we set this equal to 0. If you do this for your Jacobian, it turns out you can write this for any matrix. You have your eigenvalue squared minus the trace times the eigenvalue plus determinant at the end equal to 0. Okay, so we're just solving and finding the roots of this, and we're ensuring that the roots of this have absolute value less than 1. The Ralph-Hurwitz criteria are solving exactly the same equation, but are ensuring that your eigenvalues have negative real part. So this is essentially what's going on graphically. If I zoom in a little bit to see it a bit clearer, these 3 conditions are essentially giving you these 3 lines here. Okay, so this top one here is when your determinant is equal to 1. So if your determinant is less than 1, then you're below that line. We've got our determinant on the vertical axis and our trace on the horizontal axis here. These are just numbers at the end of the day, or they'll be, if you substitute parameters in, you'll get out numbers, right? This line here, we can rewrite one of our conditions to be 1 minus the trace plus the determinant is equal to 0. Just taken, subtracted the trace from both sides. Here it's the other one, 1 plus the trace. Remember the sign of these above. We had a minus trace and a plus trace on the left-hand side of those first and second inequalities. So they just give you these diagonal lines here. One of them with negative slope, one of them with positive slope. And so if we, obviously these all, they all go off to infinity in all directions, right? The region of this space contained by those 3 lines, by those 3 conditions, is this region inside here. So when all 3 of those are satisfied, we're in this side, this triangle, and that means that the absolute value of our eigenvalues is less than 1. And so if you cross any one of these boundaries, you violate one of those conditions, and therefore your eigenvalues have absolute value greater than 1. So this is an example where on this line here, the real part of your eigenvalue would be equal to 1. Your eigenvalue would be equal to 1. In fact, here it would be equal to -1. Okay. So those conditions there, they're all about telling you essentially when you move in and out of this region. Yeah.
And just to be clear, it's only stable when it's inside that, not on the boundary.
Exactly. Yeah. On the boundary, you're at the threshold of instability. So, for example, remember we're going to have solutions of the form lambda to the t. If our lambda is equal to 1, then you would just stay at whatever your initial condition would be, right? You would have something, your initial condition times by lambda to the t. So as t gets very, very large, nothing's happening. You just take 1 to the power of t. So you just stay there. So in a sense, it is, I mean, it's technically stable in the sense of it's not asymptotically stable because you're not moving towards it, but you're not moving away from it. So you stay within, stability is essentially saying you stay within a certain region of your steady state, which is true because you're not moving anywhere. But to be asymptotically stable, you have to be moving towards it. Usually we kind of just abbreviate to stable and unstable and kind of ignore the boundaries unless you happen to hit the boundary. And that's kind of like, again, one of these knife edge scenarios that we try not to focus on too much because they're not biologically realistic. A very good question. Okay, there's a bit more explanation down here about that. I'm not going to go through that now, but if you want to read through like why this is equivalent, that will describe that. Okay, the last thing I wanted to go through today is sort of linking back to the last lecture where we were talking about the Rosenzweig-McArthur model. Again, that was a predator-prey model. And in that predator-prey model, we saw something called a Hopf bifurcation, which meant that we ended up with limit cycles. So if you recall a limit cycle, I'm just going to zoom in here. A limit cycle is something like this, where we have a periodic orbit. Perhaps it looks like this. We have some equilibrium in the middle. So we're moving around in this way. And a limit cycle would mean that when we're outside this, we spiral in. And we spiral into that limit cycle. So we go something like this. And then when we're inside, we spiral out. This. So you remember these trajectories can't cross each other. In continuous time, a limit cycle is saying, okay, here, if it's a stable limit cycle, which is what we're basically focusing on all the time, we're gonna spiral out until we hit this periodic orbit where we've got this. If you move away from it, you get pulled back towards it. Think of it a bit like a racetrack. And then outside, you'll get pulled in towards it. Okay? You can't cross this green boundary. So you're getting pushed out and pulled in for a stable limit cycle. That was in continuous time. We can see something similar here in our discrete time model. We have something called a Neimark-Sacker bifurcation. I don't quite know how to pronounce that actually. And this gives us periodic behavior that looks a little bit like what we saw with our Hopf bifurcations. So here we've got a bifurcation diagram And this should remind you a bit of the logistic maps that we had at the start of the course, right? In simple 1D cases. So we're plotting what values do we see for here our predator population, our rescale predator population, as we vary this parameter A as part of the model. Okay. So we see here that we get this sudden, nothing's happening, periodic behavior, and then all of a sudden we end up with something periodic. If we plot the corresponding, see what value of A is this, 2.01, so that's somewhere around here. And we've got xt versus yt. We see we have something that looks a bit like a limit cycle, right? We're going around in this periodic orbit. But if you keep increasing that value of A, things start to kind of go weird. And this is where, again, discrete time models can be a little bit funky compared to continuous time models, right? So we end up having, first of all, this little kink goes on here. So if you see here, there's a slight change in the slope. It's sort of going down and then it's kind of kinks away. When this happens, our trajectories kind of go a bit funky and we end up with something that looks like this. So here, things are starting to kind of break down a bit. We then end up going through this region here. And this region, we're no longer kind of going through smoothly through lots of values, or relatively smoothly through lots of values. Here we're jumping between different values. So there's a finite number of values that we're jumping between. And this is a bit similar to, when we saw like 2 cycles and 4 cycles and 8 cycles in our logistic map. Okay, you're going back and forth between a certain number of values rather than kind of smoothly going between lots of them. So that's somewhere in here. And then finally, we end up with chaos. What's this, 2.38? So here, basically, we've got this region that's bounded. There's some boundary here. We're not going to every possible value and combination of X and Y, but we're kind of going all over the place within this region here. So we end up with chaos again. So I'm not going to test you on this, okay? I just wanted to make you aware that some of the behaviors that we see in our continuous time models, we get similar things or analogous things in our discrete time models. I'm not going to test you on the conditions for when we get these, or I might ask you a question, say, what's this called? What's the analogous thing? But I'm not going to, or to identify it from a graph, but I'm not going to test you on, prove that this model has a Neimark-Sacker bifurcation, okay? It's just to demonstrate that there's something akin to Hopf bifurcations. Okay, that's it for today, unless we have any questions. I put up a self-study problem here. We're asking you to use the jury conditions to find the stability of our trivial and semi-trivial equilibrium, and then to show that these conditions must be true for our non-trivial steady state to be asymptotically stable. I'll make a note. This, I would say, is probably quite a challenging question. It's definitely a little bit more involved than most of the things I would probably ask you. So have a go and attempt it. But if you don't get it, don't think, oh my God, this is going to appear on an exam and I can't do it. Okay. So have a go at it and see how you get on. I have office hours now as well, by the way. So any other questions? No? Okay, if not, I'll see you on Monday. Have a good weekend.